Welcome back. Through the magic of modern technology, our solver is finished, and it took no time. It took about 3 minutes actually to run this. You'll see on the info here, it looks like 3 minutes and 21 seconds to run on my old computer. If we start to look at some of our pressure cut plots as it was running, you'll see this, that we have much less low pressure developing lift across the top. We still got quite a bit of pressure on the bottom, which is a result of that deflective force. And if we look at the velocity vectors now, we start to see exactly what we saw in that wind tunnel test. We see that turbulent airflow off the trailing edge because we're at a higher angle of attack. So let me close the solver. Let's go back to our model. Now you'll see my results here, that my results load up, but I don't necessarily display them. So I have to click and show the results that I want. So there's my first result. This happens to be my pressure. And you'll see again exactly what I talked about. Not very much of a lifting force, just a little bit on the leading edge. And if I actually show my velocity and turn off my pressure, you'll see exactly that. Now you'll see in the ISO lines here, the vectors, you'll see that turbulent airflow, and you actually see the air going the wrong way. So the air is going forward as opposed to following the wing. So that's that big vortice and the huge vacuum that we're dragging along, all that induced drag, and that's why your string's picked up. So we're predicting that. If I turn off my velocity cut plot and turn on my surface plot, again, exactly what we expected to see. We have very little lift being created on the wing, and we have quite a bit of pressure. Most of it is centered along that front and midpoint, mid-span there, and that's all that deflective pressure. So pretty much exactly what we expected to see. So that is doing a very simple computational fluid dynamics on a very simple wing for conditions that we saw in the wind tunnel. So our takeaway from this is, in our foil sim, we could create a wing and estimate what it would do in terms of lift and drag. We could design a wing or take a designed wing and fly that wing in our wind tunnel and see physical things like lift, drag, alter based upon angle of attack and speed. And we could see a stall developing as we got to those extreme angles of attack by the thread starting to pick up off of the wing. Now, we didn't really see fully developed stalls on any of our wings, and the reason that we didn't see those in the wind tunnel was we were only flying up to about 50 miles per hour, so that we didn't have failures of a mount point. If we were to fly those wings faster, we would be able to develop full stalls on them. So as it is, our laminar flow stayed pretty consistent all the way up to 25 degrees angle of attack, simply because we had such low airflow over it. If we were to fly those closer to what they're designed to fly at, like the P-51 wing, not designed to fly at 50 miles an hour, more like 150 miles an hour, we'd see more characteristic L over D curves on that. So that's our takeaway. We can now take that exact same project, put it in a SOLIDWORKS, and we can predict exactly what will happen to that wing in any condition, even these low, slow flight regimes that we saw in our wind tunnel. So save this project and take the screenshots that are indicated. I'd like you to get a screenshot of all of your tests. Basically, your test showing a 10 and 25 AOA, and then we're looking for those plots of the cut plots of pressure, and we want to basically show that. Okay, I have a screenshot there, hide it, screenshot here, hide it, and if we want to reactivate our 10 degree AOA, just click activate, and you'll have to load the results. Again, I can screenshot pressure, hide it, screenshot velocity, hide it. Compare those two. We'll discuss it in class. Thanks for watching. Hope you enjoyed this first foray into SOLIDWORKS fluid dynamics and basically using SOLIDWORKS Flow. Next, what we're going to look at is our supersonic ping pong launcher and look at some of the fluid dynamic characteristics that go on with a vacuum propelling a ping pong ball down a tube. You'll be surprised how fast it goes. Thanks for watching.